Hey there, everybody. Welcome back to another Chem Complete episode. And we are continuing our organic to Friedel-Crafts reactions for benzene. And this particular reaction today that we're going to take a look at is the Friedel-Crafts acylation. So we've seen the alkylation, which is where we added just a generalized R group to our benzene ring. So now with the acylation, we're going to add basically a keto group onto the aromatic ring. So we start with an aromatic ring, and what we'll end up with is that aromatic ring having a carbonyl with some R group. So it's basically this functionality here. You could call it the acyl group, or this is a keto functionality that's coming off of the ring here. And this is accomplished in a somewhat similar fashion to the alkylation. What we're going to use is R, and R can be whatever carbon group you want there. But we're going to use this functional group right here. This is something that you may recall back when you were starting out in terms of functional groups. This is a acid chloride. It is a type of carboxylic derivative. And the acid chloride is very reactive because this chlorine makes a great leaving group. So we will also use AlCl3 to help with our coordination. So the same generalized process is going to occur at the beginning here, which is I will take my acid chloride, and the chlorine group is going to coordinate with the Lewis acid, right? The aluminum trichloride. This would be partially positive, partially negative. This is going to go and create AlCl4 with the minus charge. And then this also creates a acyl cation, acyl cation. And this looks a little bit weird to students if they're not used to seeing this. So this ends up appearing like this. So it's really a carbonyl that carbon only has 3 bonds, and so it is a type of cation that we have. Now, we should mention that this is resonance stabilized. So as weird as this may look, I also have the resonance form of this, which is why it will so readily form that, and the fact that chlorine can leave. I can come satisfy the plus charge by doing this. And what I would end up with is a carbon that doesn't have a charge. The oxygen sort of overextended itself and gave a lone pair of electrons to the carbon to get rid of the plus. So now the oxygen would have a plus. And we would definitely say, because oxygen is more electronegative, that this would be the minor contributor here, and this would be the major contributor as far as the resonance forms would go. And I could, of course, go back up and reverse this to my other resonance form, where I would probably be spending most of the time in terms of the electron density. So, if we want to consider how this is going to work from an aromatic reaction perspective, we're going to have our aromatic ring. We will have the acid chloride. We're going to take a look at the mechanism here. Along with AlCl3, we need our Lewis acid catalyst. And then we will end up, getting a little sloppy with my benzene ring here, then we will end up with C double bond O R. And you can probably guess how this reaction is going to occur here. So I just showed you the first step. What we're going to end up with is this intermediate, the acyl cation, and this is a great electrophile. So this will be attacked by the aromatic ring. And the same general process occurs. So all of the sort of opening steps have been a little different. With the nitration, we had to form the nitronium ion, but these all occur in 2 basic steps that are, number 1, form your electrophile and make it a real good electrophile. And then number 2, once that electrophile is formed, go ahead and reach out with the pi electrons from the aromatic ring and you will attach your group. So we have this here. Don't forget your hydrogen. That always needs to be there because when we finish this off, right, we have AlCl4 negative. And so right here, that'll grab the hydrogen. This will go back to form the aromatic ring, and we're all set. We've returned the aromaticity to the ring, no problem. So very useful reaction. Keep in mind this is an electron withdrawing group. Okay, but the ability to add carbonyls as well as just regular alkyl groups is very useful. Now, the one thing I really want to mention about this, and this is going to be a shorter video than the alkylation, is because for this specific lesson, there are no major limitations. No major limitations. So if you remember the alkylation, okay, in that video we said, oh, well, you can't have amines, you can't have electron withdrawing groups, you're going to get polyalkylation. It just went on and on with all of these sort of caveats to using the alkylation. And here we don't have any major limitations, and so this is nice because we can just go through, we can do this. This is a deactivator, so that's one of the reasons you won't get the polyalkylation here, or I should say polyacylation, because you're not really making the ring more reactive, you're making it less reactive, so then the remaining benzene in solution will go after these initially. So very useful reaction, pretty similar to a lot of the other ones we've seen. So to just give you an example, we could have an aromatic ring, and let's say that we're interested in adding the following: CH3, CH2, C double bond O, Cl. So the keto portion should be over here to the left. Okay, and then you have your Cl on the right. That Cl would coordinate with the AlCl3. And so what I would end up with here would be C double bond O, CH2, CH3. Okay. One point that I should mention here that a lot of people come across when they have these sorts of lessons, if you've seen the acylation in class or anything like that, is that you can take these and you can reduce these compounds down. So a lot of different reagents are used sometimes when you're attempting to do this, but one of the most common ones that you're going to see in order to do this type of a reduction would be to use the classic H2 and platinum, right? So that's one that we saw back when we did hydrogenation. Sometimes you may see this as palladium instead of platinum. This is when you have an aromatic ring, okay? Kind of like we saw the oxidation that we could do. You can bring this down to CH2, CH2, CH3. Okay, and that's nice because we said with the alkylation that we could not attach a group like this. It would end up rearranging itself. And so this right here is an example of how I could get the propyl group on here without having to worry about that rearrangement that I would find with the alkylation. So very important note that you can do a reduction here, right? I can reduce my C double bond O group into CH2 and continue onwards from there if I'd like that alkyl group. So very nice reaction. This sort of wraps up the Friedel-Crafts between the alkylation and the acylation. So there is one more major reaction we're going to take a look at, and that reaction is a nucleophilic substitution reaction. Most of these have been electrophilic, not nucleophilic, right? We create electrophiles such as C double bond O R, and it has a plus. That's an electrophile, right? Br plus, that's an electrophile. NO2 plus, electrophile. So the last reaction we're going to look at next time is what if I have a nucleophile, right? So what if I have something like minus OCH3 and this wants to attack the benzene ring instead of the benzene ring attacking one of these? It's possible. There's sort of stringent conditions that have to be set up, and we will take a look at that in the next lecture as we sort of polish off the aromatic reactions. So please remember to like, comment, and subscribe if you found this video helpful. I am happy to take any questions from the comments section. Subscribing will be the quickest way that you will be up to date if I release new videos, and I will try to keep getting those out there for you. Otherwise, I hope you guys have a fantastic day, and I will see you for the next lesson. Thanks for learning with me.